So in our last example, we solved for a passband filter design using the pole zero method, and we realized two things. When we are designing for a filter in the real world, we want something to work with in the real domain, and secondly is that we usually want our zeros to stay on the unit circle and our poles to stay inside the unit circle. That's the whole setup for the design, so that our design will follow some convention. Okay, but in this video we are going to take another example, and the solution is actually not very different from the previous one. So let's get started. So we are told that we have to use the pole zero method to calculate the coefficients of a notch filter, right? A notch filter is more or less a stop band filter, so it will stop a particular frequency and allow all other frequencies to pass. It's like more or less the inverse of a pass band filter. A pass band filter will allow certain frequencies to pass and stop the rest. Okay, so and we are to design to meet the following specification. We have a notch frequency of 50 hertz, right? I mean, that's the frequency we have to attenuate. We want to remove 50 hertz completely from the signal coming. Then it has a 3 dB width of 5 hertz, okay, and plus or minus 5 hertz. Now, when you hear a 3 dB width of plus or minus 5 hertz, it means that the bandwidth is 10 hertz, okay, plus or minus 5, the difference is 10. And the sampling frequency is given as 500 hertz. Now, these are important information you are looking for in solving this question. So let's read their solution. So it says to reject the 50 hertz component, we place complex zeros on the unit circle corresponding to 50 hertz. That is at this angle. So this is what it's saying. It seems that this 50 hertz, right? When you convert it to the angle format, you get what? 50 over 500, because 50 hertz is the notch frequency over the sampling frequency times 360. That is what we have been doing so far, right? We are just converting it from the frequency plane to the z plane, okay? And when you do that, you get 36 degrees, okay? But I realize that 36 degrees doesn't lie on the real axis, okay? So if you have the real axis, you realize that usually the angles that lie on the real axis will be 90, will be 180, 270, or maybe 360, right? Those angles. But 36 degree will lie maybe somewhere around here. So it will have both real and complex imaginary component. So it is complex. Okay. So seeing that, then it means that we have to also find its conjugate, so that at the end of the day, when you combine the conjugate pairs, you get out a real component. That's the whole procedure of our pole zero design mechanism. Now, the issue is we got only one angle, 36 degrees. So we place a pole at the opposite side of what minus 36 degrees to get the conjugate. Okay. So it means that our angles will be one at 36 degrees, the other at minus 36 degrees. But see, the issue here is that we've now gotten our zero, but we don't have our poles. Okay. And it's actually simple to get a pole for the notch filter. You remember that in the pass band filter, you were strictly defined for frequencies at which you are supposed to see zeros and frequencies which you are supposed to pass. Okay, so they define it for you. But in the notch filter, the thing is you're only trying to eliminate that frequency. Okay, so you put your poles at the same place to just balance the zeros. Okay, so to achieve a sharp notch filter, on either side of the notch frequency, place a pair of conjugate poles at the radius less than 1, yes, within the unit circle. So that's radius less than 1. The reach of the notch filter is determined by the location of the poles. Okay, so in the notch filter design, it's more or less like how you locate the poles relative to the zero, so determine how sharp your notch will be. So for example, you can have a notch filter like this, so, or you can have something like this. I realize that this one, the transition here is sharp compared to this one. Okay, and that's all based on the relative position of the poles and zeros. Okay, so that's what the whole sentence is talking about. Okay, so we'll place our poles at plus or minus 36 as well, so that we get a sharp response. Okay, we were not asked to extend it or anything else. So that's what you see on the unit circle. Now probably you might be asking where we are getting this 0.937 from, and you remember that radius is given by 1 minus the bandwidth over the sampling frequency times pi. This is from the previous video. Okay, now the bandwidth, I told you that you were given a 3 dB notch width. That's the width of this small region, right? That width should be what? Plus or minus 5 hertz, right? So the bandwidth should be what? 10, right? It means you plus or minus 5 within that frequency range. Okay, so the bandwidth should be 10. So you get 1 minus 10 over the sampling frequency is what? 500 times pi. All right. Now, once you punch this, I am sure you get 0.937 in your calculator, right? And that's the 0.937. The 0.937 represents the radius of the pole. Okay, the radius of the zero is on the unit circle, so the radius is 1. That one we don't even need to calculate, but the radius of the pole is what we are evaluating. Now, once we do that, then we are left with writing our equation. And by now, you should be very conversant with the equation. The equation is z minus a, where a represents the zeros. So z minus a1, z minus a2, up to z minus a whatever, all over what? Z minus p1, z minus p2, up to z minus p whatever. Okay, now the a1s, a2s here are your zeros, and your p1, p2s here are the poles, right? I'm very much aware that that one was in the previous video. So to evaluate this now, remember that you had an angle of 36 degrees. Okay, so when you are representing it in the Euler's form as a complex number, you have what? For the zeros, so for the zeros, you have e raised to the power minus 36 I. Now here they use j to represent it. It's the same thing. I mean, whether I or j, it just depends on where you are using it. But usually, this still means that it's a complex kind of thing. Okay. So remember that we had 36 I, right? 36 degrees. Yes, so it's here supposed to be positive I for one of the zeros, but the conjugate to be what? Minus 36. So the zeros will be out e raised to the power 36 I and e raised to the power minus 36 I. Okay. So there'll be two zeros, right? One at positive 36, one at negative 36, just like we discussed here, right? And that's what you see. So those z minus a1 times z minus a2, that's what you see at the top. So z minus a1 is e raised to the power minus 36. E2 is what? E raised to the power plus 36, right? So you have been able to get your zeros or your numerator of the expression. Then the poles, the same thing. Now remember, when I write e raised to the power minus 36 I, it means that what? The radius is 1, right? The real expression is e raised to the power minus I theta. Hope you remember that, yes. But for zeros, the radius is 1. That's why at the top, you don't see any radius multiplying. But at the bottom, the radius is not 1, okay? Because we evaluated the radius for the poles. The poles are at the bottom. We evaluated the radius for the poles, and we got 36, sorry, 0.937, okay? So one of the poles occurs at what? 0.937 e raised to the power minus 36 multiplying z minus 0.937 e raised to the power positive 36. Okay, so those are the location of the poles. Yes, and they are complex. Okay, now I'm very much aware we can do this expansion, but I mean, for the sake of being thorough, right, let's purposely do it just for this video and see. I think let's just do the numerator. Okay, so let's just do the numerator. So at the numerator, when you expand the numerator, you get what? Z squared minus z multiplying e raised to the power positive 36 j minus z raised to the power minus 36j plus e raised to the power minus 36j times e raised to the power positive 36j. Okay, yes, and now this becomes an expression you can simplify. So you can get z squared at the outside. Now you can bring the minus z out. So you get e raised to the power positive 36j plus e raised to the power minus 36j, right? And now e raised to the power minus 36j multiplying e raised to the power plus 36j will give you e raised to the power 0j, which is 1. Hope you remember that. Yes, because minus 36 plus 36 indices, you get e raised to the power 0, which is 1. Then you can come ahead and evaluate this. Z squared. So this middle one is the one which will cause trouble. But I mean, that one, you remember that when you have e raised to the power I theta plus e raised to the power minus I theta, you get 2 cos theta. Do you remember this? Yes. So it means that we'll get minus 2 cos 36, right? And all plus 1, of course, the 1 here. So all plus 1 here. Okay. Now, the next part is just entering it into your calculator. So you just enter 2 cos 36. So let's try entering that. So let's do minus 2 cosine of 36. Let me make sure my calculator is in degrees, so 3, and I get what? Minus 1.618. So that's what is here, minus 1.618. Okay, so the final answer will be z squared minus 1.618z all plus 1. Okay, and that's the answer is here at the top. Now you can go through the same long process for the denominator. I really don't see the necessity here at the moment. Okay, yes, but once you are done with that, I mean, then you are halfway there. Okay, then now you have to express this in terms of a difference equation. Okay, and I'm also very much aware you know how to do this by now, but let's go through the whole procedure again. So I hope you are very much aware with this equation, right? This equation, right? Now this equation shows the format of our answer, right? So our answer is actually a type of this equation. Okay, and that's what you see. So our answer says that our numerator coefficient will be for the x's. So you see that b is multiplying the x's, and our denominator coefficient will be for the y. So realize that a is multiplying the y's. Okay, so just read the equation and relate the right thing with the right results. Okay, so our numerator coefficient is supposed to be for the x's. So on our numerator we have 1 first. So 1 is the same as x of n. Okay, because I mean it has no delay, it has no shift. Minus 1.6180, right? Multiplying z minus 1. Now the numerator is for x of n, so if it's multiplying z minus 1, that means you have to do what? X of what? N minus 1 plus 1 times z raised to the power minus 2, which is the same as what? X of what? N minus 2, right? So that's our numerator, right? Our denominator will be for the y's. Now remember, our denominator is such that we always have to have 1 here. Okay, so when you solve and get this answer, make sure you divide the numerator and denominator such that you get a constant 1 here, right? 1 plus anything, 1 minus anything is okay, but get a constant 1 so that you can use this procedure, else the whole thing will be wrong. So our denominator, we have a 1 here, right? That 1, it compares directly with the equation 1, so we don't touch it, right? Then we have the remaining of our equation. So realize that the remaining of our equation is what? minus 1.5164. Okay, but see, because this one is a minus, right, and the one we have here is a plus, we have to take our time. Okay, yes, take your time. So taking your time, noticing that here was a plus and here is a minus, means that anytime you see a minus, you negate it to a plus, and anytime you see a plus, you negate it to a minus. That is how you write the equation. You see, honestly, I don't like using this procedure because, I mean, you may easily make mistake. The reverse procedure, where you write it as a full transverse function and make change of subject, is better, but you let's write it. So this one will give you positive, so plus y of plus of 1.5164 y of n minus 1 plus, here is supposed to be minus, right? So minus 0.8783 y of n minus 2. Okay, and all this is supposed to be equal to y of n. That is the main equation. Okay, now when you do that, that's when you get the answer. So that's what you see. So x of n, y of n, and the other terms of the sequence. Okay, so yes, that brings us to the end of this video. You can continue to ask your question, and if you are interested in the other method of getting this equation, I think I solved it in the previous video, so you can get hands on it. Thank you very much.